So in this activity, the chi-square GOF, we're going to investigate the relationship between multiple different categories and whether they're evenly distributed or follow some predetermined population distribution. All right. I'll get into the example in a second, but what we look for are the relationships between the actual outcomes, the observed outcomes, and what we expected to happen. All right. The alpha value we use as a threshold, you can see it here, decide whether the results are significant. We use that to determine what's called a critical value. And the relationship between the test statistic, which I'll show you how to compute in a minute, and the critical value is what dictates whether or not the null hypothesis is true. The null hypothesis is a statement of some assumed relationship, previous relationship that might exist, and the alternative is what would be true if the null hypothesis isn't. That's essentially a very simple explanation of what a hypothesis test will do, in this case a chi-square goodness of fit GOF test. But in terms of practice, it's actually pretty easy to carry out. We do have to do some calculations, but nothing too crazy. I have an example here. A local police department wants to investigate if the color of cars they pull over is equally distributed across 6 colors, red, blue, green, and so on. Over the course of 300 traffic stops, the frequencies of car colors were observed and listed in the table below. Conduct a chi-square goodness of fit test at the 0.05 significance level to see if the observed frequencies differ significantly from the expected frequencies for each color. First move is to get the total, which it said 300 traffic stops, so that should be easy enough. So I'm going to do sum, and I'll get the sum of these values here, and then I'll lock it in. The expected values, if we're looking to see whether there's a significant relationship between color of car and whether or not that car pulled over, we could assume as a default that all things are equal. Like if there's 300 traffic stops, we would assume that out of these 6 colors, 1/6 of them would be red, 1/6 of them would be blue, and so on. Right? So what I would do, and that's because there are 6 different colors available. I'll take this number and divide it by 6. You're going to do a problem, I think it's in assignment 3, maybe it's assignment 1, but where we address the fact that there aren't as many red cars out on the road, for example, as there are black cars or silver cars. So there is differing percentages, and that could impact the rate at which a particular color is pulled over. But for now, we'll just assume that they're all 50, and that is what we call a uniform distribution. So what I'm going to do is compute, and I'm kind of skipping over this stuff here. We're going to jump right to the test statistic. That's what this table set of calculations in the table will do. We're going to find the difference between the observed and the expected across the board. We're going to square those values across the board, and then we're going to divide those values by whatever the expected value was, and again across the board. Once we do that, we get the sum. That sum is our test statistic. Now the null hypothesis, we assume as a default that there's no difference in the population distribution. All right, meaning that reds get pulled over the same amount of times as the blues and the greens, the blacks. You could say all the percentages are equal. You could vary it, but no difference in population distribution would work, because the population distribution should be that they're all, in this case for the sample, 50 a pop, but it should be however many there are in total, divide that by 6, and that would be how many you would expect to have for each color, right? The alternative would be pretty much the same thing, just now it's some, SOME, difference in population distribution. All right, we don't know how much of a difference, we would just know that there is a difference. The alpha value, they told us in the problem, the significance level is the alpha, 0.05. The critical value, so we get this by selecting equals, and we're going to start typing in chi. You'll see an option for chi inverse, all right, right-tailed chi-squared distribution. All right, we're going to put in the alpha value, 0.05, and the degrees of freedom, however many categories you have, subtract 1 from that, and that's your degrees of freedom. So 1, 2, 3, 4, 5, 6. So we'll do 6 minus 1, which is 5. It's not always going to be 5. It's going to depend on how many categories that you have. All right. The rule is if the test statistic, and that's this number here, is greater than the critical value, then we reject the null hypothesis. So we're going to reject the null hypothesis. I'll just write reject the null. And then we draw our conclusion. All right. So we would say there is enough evidence. There is enough evidence to reject the claim, that's the null hypothesis, that there is no difference in the population distribution. Now, it's specifically of car color. We always address what the alpha value is, so we'll say at the 0.05 significance level. And then we make a quick statement about what that means. That means that there is a significant difference among the colors of cars, I'll just say, that are pulled over. All right, and that would begin the conversation of, okay, so which one is the one that's getting pulled over more or less frequently? Why might that be the case, and all that good stuff. All right, but this is, hypothesis testing are usually the beginning of the conversation. It really points out a problem that might exist, and then you investigate further and really kind of flesh out what the cause of that might be. All right, so at this point, you'd move on to assignment 1, which is asking you to pretty much do the same thing. They give you outcomes for rolling dice, run through it. We're going to determine if the die, based off of these outcomes, is fair. If a die is fair, it means the expected values would all be pretty close to one another or exactly the same, because when you roll a die, you should have an equal probability of getting the numbers 1, 2, 3, 4, 5, and 6. After that, you'll get a die, right, and you'll roll it a bunch of times, 60 times in particular. You'll record your own data and run through the same process. Then for assignment 3, here I give the percent of cars that are red out of the population. So you'd get your total and multiply that total by the different percentages. All right, so in this case, I forget, I think it was like 300. It might be 200, but whatever number this is, multiply by 0.1, put it here, multiply by 0.15, put it here, and so on, and then carry out the process. And the last assignment is based off of the data that you collected when you walked around the building. All right, so if you chose type of music, you might put like country, R&B, or jazz, and then your observed values would be how many people selected each one, right? And then do the same thing, get a total. Expected values should be, we'll operate under the assumption that it's uniform. So take your total and divide it by how many categories you have, and those will be your expected values, and then you just carry through the rest of the way.